Hi, and welcome to a video on sequences. And what we're going to be looking at in this section is really meant for a Calc 2 class and just the beginnings of what a sequence is, how do we write it out and list all the terms, how do we find patterns for it, and then how to determine if that sequence will converge or not. So let's start by just reading here and looking at what a sequence even is. So a sequence can be thought of as a list of numbers written in a definite order, and we want to keep the order like it's shown. So 1, 3, 5, 7, or you'll notice here the bracket notation, which is a little bit different than the first way I wrote it. 1/2, comma 2/3, comma 3/4, and then you'll notice at the end we have that nth term pattern. Now n doesn't necessarily have to represent that last term, that could represent any term in that sequence. So a sub 1 is typically called the first term just when n equals 1, but please do note that our first term does not have to be when n equals 1. It can be however we define it to be when we get to series, especially that will become important. The domain of a sequence is the set of all positive integers, meaning this will be, for example, n equals 1, 2, 3, 4. The value of the sequence at a given n value is the range. So 1/2 is the range, 2/3 is part of the range, 3/4 is part of the range, etc. And so here's some different ways we can write them out. So we are asking you to write out the first 5 terms of the following sequences. And what we're going to do is give you a pattern for that. So then you're going to say, okay, a sub 1, or my first term, will be putting in 1 for n. So that will be a -1 times 1 plus 1 all over 3 to the 1, or a sub 1 will be -2/3, and I'll write out my list as I go up here. And then I do the same thing for a sub 2. So I have -1 quantity squared, which will be +1 times 2 plus 1 all over 3 squared. So this will be a sub 2 is 3 over 9, or 1/3. And then I keep going. So let's do a sub 3. So it'll be a -3 plus 1 all over 3 cubed. That denominator is going to grow pretty big pretty fast. Or if I figure this out here and do this computation, it'd be -4 over 27. And oftentimes they will ask for probably more terms than you'll want to find, just because it becomes very sort of mundane here. Put in a 4 for n, I get a +1. Put a 4 for n, and again, everywhere you see an n, there's 3 of them. So 4 plus 1 all over 3 to the 4th. So that would be 5 over 81. And if I put a 6 in, or excuse me, a 5 in, I was looking at the 5. So for my last term, it'll be -5 plus 1 is 6 over 3 to the 5th. You are always welcome to leave powers, but this will actually reduce. So this will be -2 over 81, because it's -6 over 243, and that reduces. Okay, so that is what you're doing when you're given sort of this pattern for each nth term. And what you'll notice is I could now say, what is a sub 27? Well, we're just putting 27 in for n and figuring out what that term is. So these are sequences that are written in this sort of pattern way, not in a recursive way. So this is an nth term formula, the way these first two are written. The second example that I went through there just has a sub n equaling cosine n pi over 6. So you could just see what those maybe look like as they're all written out. This first one is also called an alternating sequence, because if you'll notice this -1 to the n, every time it's odd, it's going to make the term negative, and if it's even, it's going to make the term positive. All right, so what does a recursively defined sequence look like? Well, here it is. So what they're going to tell you in this case is a sub 1, so here's my first term, and then n plus 1, so a sub n plus 1 really just means next term. And a sub n minus 1 is going to mean previous term. So sometimes we can define a sequence or a list of numbers based on what the next term is going to be. This is not as convenient for us because if we want to find the 27th term, we have to know all the first 26 before it. So it's not quite as helpful in the long run. But it's pretty easy to write the patterns, I will say. But so if a sub 1 is 2, I've already got my first term. So when I'm finding a sub 2, that would be a sub 2. That means n is 1, right? Because 1 plus 1 is 2. So that would be a sub 1 over 2 plus a sub 1. And we know a sub 1 to be 2. So 2 over 4 gets us 1/2. And because there were a lot of 2's all over the place, I'd like to do this one more time with us. So a sub 3 is going to mean that it's, if n plus 1 is that next term, a sub n would be my current term. So that will be a sub 2 over 2 plus a sub 2. And a sub 2 we found to be 1/2. So the other bad news here is that if you find one of these terms incorrectly, every term after that is going to be incorrect. And I like to just multiply by some number that will get rid of my complex fraction immediately. So I'll multiply the numerator and denominator by 2. So I get 1 over, I have to distribute that 2, 4 plus 1. So this should be 1/5. And then I continue going. A sub 4 is a sub 3 over 2 plus a sub 3, and I knew my a sub 3 was 1/5. And so I get my list of numbers there. Now, recursively defined sequences are pretty easy to write because you're just basing your current term off of your previous term or your next term off of your current term. So let me write what those are. So if a sub n means current term, right, any term that you are talking about, if you're moving forward and sort of going down the list towards your next term, that would be a sub n plus 1. If you are looking backwards, that is going to be a sub n minus 1, and that means previous term. And so those will help you as you're looking through these sequences as well. So what you're going to have to do is you're going to have to write some formulas for the nth term of any sequence. And so you're certainly welcome to pause this video and read through all of these. Just some key things here is that, the n minus 1 is previous term and that n plus 1 being next term is a big idea. If it's alternating, you might want to use this -1 idea. And then we'll talk about all the rest here as we go through. So find a formula for the general term of the sequence, assuming that the pattern of the first few terms continues. So what I see here is just a listing of various numbers. They give me 4 of them. That should be plenty for my pattern. You'll notice the ... which means it's going to go on infinitely long. And I would like to see all of them as fractions, and some of them are. I'd like all of them to be. And underneath all of these, I'm going to put the term number because that's what you're going to compare this to. If you're trying to write an nth term, like a pattern for this sequence of numbers, you're trying to compare the actual number in the sequence to the term number, not to the previous number back and forth per se. So here's what I notice. I notice that my numerator is always a 1, right? No matter what term you're on, your numerator is always a 1. And then one way that you can look at this is, what's the relationship between 1 and 1, 2 and 3, 5 and 3, 7 and 4. You might not see it as being obvious. if you look at these denominators one after another, the only reason that I want you to look at them is there a constant increase in them? And there sure is. A constant increase of 2, or if you're repeatedly adding 2, that turns into multiplication. So I'm going to start this with 2n. Because if I add 2, for example, 15 times, I don't have to add 2 15 times. I can just say, what is 15 times 2? 30. Okay, so repeatedly adding a constant value of 2 in that denominator will start me off with 2n. But then I want to compare that term number, right, to that denominator. These are not just 2n. Well, if I multiply the n by 2, how would I get 7? So if I multiply 4 by 2, I have to subtract 1 to get 7. Is that true for the 3? If I multiply that by 2 and subtract 1, do I get 5? Yes, because 3 times 2 is 6, minus 1 will get me the 5. Is that true for the 2? 2 times 2 is 4, minus 1 is 3, and 1 times 2 is 2, but minus 1 gets you the 1. It works for all of your terms. So there is your pattern. Some people are very good at seeing patterns when they just look at something. For others, this is definitely a work of art. It takes a long time. I would say take your time and really walk yourself through it step by step. There are formulas. I just caution you that when you use a formula, you might not be paying attention to what's happening. And so if you use the formula incorrectly, you might not even recognize it. All right, so again, I like to see all of these as fractions. So I'm going to put negative 3 over 1 and 2 over 1. And I'm going to write my term numbers underneath. That's an n equals 1, 2, 3. I probably should have done this in a different color, but that's okay. 5. All right, so it's natural, right, to look from term to term, and that's okay because you want to at least determine, are you adding something repeatedly? Are you multiplying by something repeatedly? Should you treat the numerator separate from the denominator, etc.? So as a general rule, I treat the numerator separate from the denominator, okay? So if I look at these numerators, I go from negative 3 to 2. Well, I've added 5. But I certainly don't add 5 again. And what I also notice is this is an alternating sequence, so I've got to be careful and make sure I get that negative 1 in there. Okay, or a negative 1 power, anyway, negative 1 to the n or negative 1 to the n plus 1, for example. So let's look at your fractions. One way to get, I'll just highlight this, what I'll call my first fraction here, even though it's not, in green, and I'll highlight the next one I'm going to look at in blue. Let's just look at these two alone. Is this sequence what we call geometric? And indeed it's going to be. Why? Because I'm multiplying by a negative 2 over 3 repeatedly. Multiply by a negative 2 over 3. Now does that work when you start? If I take negative 3 and multiply by negative 2 over 3, I in fact get 2. So yes, this worked every single time. I can check it every single step along the way. So if you are constantly multiplying by negative 2/3 forever, repeated multiplication, the definition of that is a power. So what I'm going to start with is I am repeatedly multiplying by negative 2/3, so that's an exponent, n, right? N times. I don't know how many times. Well, what are we repeatedly multiplying something by? Let's start with the first term and just see if this works. Okay? So now check it, because again, you can't just guess, right? You have to check. So if I put a sub 1, if I put a 1 in here, I get negative 3 times negative 2/3 to the first, or in other words, I'm saying that my first term is 2. Well, your first term is not 2. Your second term is 2. So what that means is when you put n equals 1 in, you actually got your value for n equals 2. So I sort of want to back this up 1. I want to get that -3 term first, not the 2. So I'm going to back this up or look at previous term. Okay, so n minus 1 instead of n, and let's check this now. A sub 1 would be -3 times -2/3 to the 1 minus 1. I'm ahead of myself here. 1 minus 1 is 0. -2/3 to the 0 is 1, which leads me -3 times 1, or -3. That's my first term, so this works. Again, there is a formula if you know that a sequence is geometric, but if you understand that repeated multiplication becomes a power, you'll probably be okay. And then what are you repeatedly multiplying by? Well, you have to have a term to start with, so just throw your first term in there. That's how the formula came out in the first place. Okay, so I'm going to look again at my term numbers here so I can compare them. And as soon as you're writing them down, you're probably seeing something familiar in that denominator, right? So I see again my numerator and denominator as kind of being separate entities. And in my denominator, I'm going to show you two things here. I can see that all I'm doing is really adding 1 to my n, right? So I can say, yep, it's n plus 1. Well, why else is it n plus 1? I'm going to put a 1n plus 1 because it really doesn't matter, but I'm going to show you how that might be helpful. I have a constant increase. If you compare one denominator to the next, I have a constant increase of 1. And so what I would start with is 1n, and then I have to add or subtract something to when I put n equals 1 in so that I get my first term of 2. So I need to add 1 here because this 1 plus 1 would be 2. So I can figure it out sort of loosely as well. Again, your pattern writing is going to be dependent on your ability to sort of look at this and see various things. Some of you are going to be very formula driven, and that's fine. I gave you those formulas above. So 1n plus 1 or n plus 1 really doesn't matter. It sort of looks like absolute value bars, so I'm just going to write n plus 1 if that's okay. All right. So then in my numerator, I can see that, yes, I'm alternating because you see your first term's positive, second term's negative, third term's positive, fourth term's negative, etc. So this looks like it's going to be an alternating sequence, so I can take care of that right now with a -1 power. Now you can't just say -1 times something because that's always going to make an odd number then because this is -1 to the first. So that's not what I want. I want this to alternate, so I either want this to be -1 to the n, or you can use next term or previous term because if it alternates, n is right there in between. So you can use either one of those. So let's see. If n is 1, we want our first term to be +1/2. So -1 to the n would be negative if n is 1. That's not what I want, so I'm going to add 1, or you could subtract 1 to get the previous or the next sign in there. So this is my alternating piece, so that's taken care of. My n plus 1 for my denominator is taken care of, and you can put it in parentheses if you don't want to lose it. Now I need to figure out just these values in the numerator. How do I go from 1 to 4 to 9 to 16 to 25? And if you compare them to the term numbers down here, that might help as well. Well, just look at what you're adding each time. I'm adding 3, then I'm adding 5, then I'm adding 7. Again, I've already taken care of the alternating part, so that negative doesn't come into play anymore. And then I'm adding 9. I have an increasing increase, right? I'm not constantly increasing by 3 or constantly increasing by 5. I have an increasing increase, right? By 2 every time. This is actually the definition of your squares right here. So if you see an increasing increase, you probably have some polynomial function up there, right? Some x cubed or n cubed or n squared minus 4, something of that nature. So if I look and now compare, what is the relationship from 1 to 1? Well, I don't know, that's not always as obvious. What's the relationship from 2 to 4? Again, 2 can be ambiguous, so I don't want to look at that. But how about 3 to 9 and 4 to 16 and 5 to 25? Oh, that's just n squared. And so there's my pattern for that one. You can certainly check them the same way that we wrote them out before. Okay? That probably would be helpful, like a sub 1 equals, and make sure it matches. Okay, let's just quickly talk about the convergence and divergence of sequences, and then in the next video we'll find a whole bunch of them. So a sequence that's given has a limit as n approaches infinity. You just have to find it. So if it does not have one value, right, that it is approaching, so you found your limit and it's infinitely big, or you found your limit and it's not one finite value, then we would say that that sequence diverges. Okay? If we can look at our nth term and say, oh, I think our sequence is going to look like 2/3 as n approaches infinity, or I think our sequence, my last term, is going to look like 0, then we can say our sequence converges because I know what the last term will look like. It's some finite value, and I can tell you exactly what it is. Okay, so you can use a graph to tell you this, but we're going to actually look algebraically. But if you want to check some of these and you're unsure, this is one approach. You're looking as n approaches infinity. So what you'll notice now is n is sort of my x-axis or input, and a sub n is my output. So all I'm really doing is saying plot your first term, plot your second term, plot your third, fourth, fifth, sixth, and seventh terms, and then it keeps going beyond that. So plot those terms and see if you can find a horizontal asymptote, or what you might think your graph is approaching. So they asked the question, does it appear to converge or diverge? This is the graph that they were giving you. And so I would say, yes, it seems to be approaching 1. So as n is approaching infinity, again, we're only looking until about, I don't know what this is, maybe 12 or 13 here. That is not close to as n approaches infinity. The closer you get to infinity, though, the closer that term or your range will look to being 1. And so how can we do that? Well, we're finding limits. So we just need a couple reminders before we go to that video on limits. Here are some pre-calc reminders on limits. So if we're looking at this given function here where I have some rational function, and I'm going to look at them as separate, f over g basically. So we can compare the degrees. Now this was how you learned before you learned L'Hopital's rule, so you could certainly use L'Hopital's rule for anything that's infinity over infinity and prove this as well. But if the degree on top, the highest powered term, is the same as the degree on the bottom, then your function was said to have leveled off at the ratio of those coefficients. So I would say that's my limit in that case, 5, 6. So as n approaches infinity, I do have a horizontal asymptote, and that would be 5, 6. So if the degree of the top is greater than the degree on the bottom, well, there's no horizontal asymptote then, so my function in this case grows to positive infinity, so that would be my limit. My limit would be infinitely large, but I would say that that sequence, if I had to talk about the sequence converging or diverging, I would say that sequence diverges because I can't come up with one value where I could tell you exactly what that so-called last term, that nth term, would look like. And then lastly, if the degree on top is less than the degree on the bottom. So here's 6n. So again, we're talking about largest power or highest powered term. So degree on the top is less than the degree on the bottom. That would level off at 0. Again, L'Hopital's rule would prove that as well. So that would be my convergent sequence. So last reminder here before we get to that convergence or divergence video. If you have an indeterminate form, L'Hopital's rule will help you if you have infinity over infinity or 0 over 0. There are 7 indeterminate forms that we have talked about, and these are the 2 that work for L'Hopital's rule. So if you see a ratio like this, find this limit. This will be common. You cannot just say, oh, well, the denominator is bigger. Well, these technically are both infinitely big. So then if that's the case, you're ready to use L'Hopital's rule. That's my notation that I am changing this limit, meaning L'Hopital's rule said I can do the ratio of their derivatives, and that will have the same limit as the ratio of the original functions. So I can do the derivative of the numerator over the derivative of the denominator. Then I would try to substitute in my infinity for n. Oh, that's still infinity over infinity. And I can do it again. So I can say, let's do another iteration of L'Hopital's rule. Limit as n approaches infinity. If you don't have a limit, this does not work. So derivative of the numerator is 2, derivative of the denominator is e to the n. Now I know I can't use L'Hopital's rule anymore because I don't have infinity in my numerator, and there's no rewrite I can do to get infinity in my numerator. So this should be ready to be evaluated. So I would say something like 2 over e to the infinity, or some of you have learned big little logic, 2 over really, really big will level off at 0. And once we start talking about that in a sequence sort of form, we'll talk about that sequence converging at that value. I hope you found this video helpful. Thanks for watching.